All right, we're going to begin in just a moment. So I'm working on the lighting here. I'm trying to get all the angles proper. Let me get rid of this text. All right, so as the text here says, we're going to be discussing group theory and Cayley's theorem, which is a main theorem in group theory. Let me just get rid of that. And we also just made a Discord. So the Discord will be good for anybody that just wants to ask questions. Maybe you have questions from your class at college or high school or whatever math you want to discuss. So we have a Discord now, so that'll make it easier for you guys to talk to me or talk to others about any type of math problems. Yeah. So today, let me write on the board. Where did my markers go? Okay. So this is lesson 2. And again, this will be on YouTube, so I will upload this later if you're watching this in the future. So this is lesson 2. And this will be titled Group Theory. So we're going to just continue talking about group theory. Let me see if I can get this closer. Might be better. So we'll be discussing group theory more, but specifically Cayley's theorem. Okay, and Cayley's theorem, we briefly talked about it last time. It's this isomorphism that you get where there's a mapping from the group into a certain symmetric group that sort of permutes the elements of the group. So let me just remind you of what the statement was for Cayley's theorem. So Cayley's theorem says if we have a group right, so any group, in particular you might want to think of it as like a finite group, but really the theorem holds more generally. It's just that the symmetric group is a lot more tangible. It's a lot more easy to think about when the number of elements is finite. So if G is a group, let G be a group, then there always exists a group homomorphism which I'll call phi C for Cayley's map. So it's a group homomorphism from G into the symmetric group on the number of elements that G has. So there's a map from G, and the way we'll write this is as S with a little underscore, and it's the number of elements in G, or the size of G. So I put these little brackets around G to denote the size or the cardinality. And the last time we said that the map is defined by we take every element and we send it to the bijection, which sends every element in G to its left multiplication by that element. So another way to say that in different languages, we take G, an element in the group, and we send it to a permutation where if we list all the elements of G out, like G1 through Gn, it maps them to G times G1, G times G2, G times G3, and so on. So you're multiplying everything on the left by G. And last time we said we could write a permutation explicitly by just saying where every element goes. So here I'm going to say G1 goes to G star G1. G2 goes to G star G2, and so on. So that defines the permutation. It's a permutation defined by left multiplication by G. And remember, when I say multiplication, this is like an abstract sense of multiplication, where this is an abstract group. It has some binary product that satisfies the axioms, but we don't really know necessarily anything more about it other than that. Okay, so this is basically the statement of Cayley's theorem. For any group G, there's always a group homomorphism, G into the symmetric group. And it's actually never an isomorphism because this symmetric group is a lot bigger, but it is an isomorphism onto the image. So everything that's hit in the image of this map, it's an isomorphism onto that. In other words, I'm saying that this map is injective. So it's not necessarily onto, but it's always one-to-one. And we could show that, but I don't want to waste too much time. Is there any questions if anybody is in the audience? So we have group theory, talking about group theory. These abstract groups are just some abstract symbols that sort of represent invertible maps, but we don't necessarily have the maps in general. We just kind of have this abstract notion of what's going on. Right. And then sort of this theorem is saying that really you start out with this abstract notion, but really for any abstract group, we can always look at it as some subgroup of this symmetric group, this special type of group of bijections. Okay. Let's see. Let me just get through a couple definitions here that are important. So we want to understand this theorem a little bit more and work out some examples possibly, or some exercises from the book. And so I wrote this down briefly last time, but let me just write it again. So group homomorphism. Right, this just means you have two different groups, G and maybe W is a different group. And I have a function between them, and it's a group homomorphism if it respects the multiplications in each group. Meaning that if I multiply things in G first, phi of G1 times G2, let's say, and then I map it through the function, it should be the same thing as if I map the individual elements first and then do the product kind of like on the way out after I've mapped them. So do the product first, map it. It should be the same thing as mapping the individual elements and then multiplying them in the output space in W. So this has to be true for every element G1 and G2 from G. So if this is true, then we call it a group homomorphism. So it needs to be true for all G1, G2. All right, so this homomorphism idea is like you're mapping subgroups into subgroups. You're mapping groups into groups. This function somehow preserves the structure in exactly the way that we just wrote. And this gives you some nice properties, like the image of the map you can show as a subgroup of W. The kernel of the map, or everything that maps to the identity in W, is a subgroup of G, and it's what we're later we might talk about normal subgroups. So the kernel is actually a normal subgroup. It's a special type of subgroup. And then an isomorphism is a special type of group homomorphism where you have this property, but in addition, you know that this map is also one-to-one and onto. So I'll just write that on the side real quickly so we don't have to rewrite everything. But in a group isomorphism is a group homomorphism, but it's in particular one-to-one and also onto. So You have group homomorphism, respects the products in the individual groups. Isomorphism is the additional property that it's a group homomorphism, but also it's a one-to-one map, meaning that two elements always get sent to different elements. If I start out with two different elements, they get sent to different elements. That's the one-to-one property, or another name for that is injective. And then onto just means that every element in the image space is hit by some element in G. So if it's one-to-one, if it's injective, it's also onto and it's surjective, then we call it bijective, right? So a group isomorphism, another way to say it is that it's a group homomorphism that's also bijective, or in other words, one-to-one and onto. All right. Right, and then I just want to write down briefly the definition for subgroup because we keep talking about it. Sort of, I'm referring to subgroup quickly, but we didn't really give it a formal definition. And then we'll go over a couple examples of subgroups in some of these smaller, simple groups. Simple in the sense that they're small and easy to write down. So a subgroup, right? In particular, a subgroup of a group is first it's a subset, and then it also has to be a group. But more precisely, a subset H inside of G. So G is our group, H is some subset. We'll say that H is a subgroup if it has these three properties. So first, so a subset of a group is a subset of a group is a subgroup if it's closed under the product in G, meaning that if I take any two elements from the subset and I multiply them together, I should get something else in that subset H. So I shouldn't leave the subset when I'm multiplying elements in it. It should be closed under the operation. Then the second property is that it has to contain the identity. So in particular, it can't be empty. There's no empty groups. So 2 must contain the identity of G. So H must contain the identity. And then the last property is that so the first two properties say that it's a submonoid, and then for it to be a subgroup, it must also be closed under inverses. So for every element in H, its inverse has to also be in H. So if G is in H, or if I'll just say little h. If little h is in H, big H, then that means that its inverse, H inverse, is also in H. So for example, you could have a submonoid of a group that's not actually a group itself. For instance, I believe the non-negative integers are a submonoid of all integers, but they're not a group since 1 is in there, but you don't have -1. So it doesn't satisfy the third property. Right. So you have this substructure, meaning that it has the same type of structure as the bigger structure, but it could possibly be a proper subset. So you might be missing some elements from G. Although you could have all of the elements in G, and then that would just mean that H equals G, and then that is one of the subgroups of a group, the entire group itself. So there's actually always two trivial, well, there's usually you just call one of them the trivial group, but there's always two subgroups for sure of a group, which is the entire group itself, and the subgroup which contains only the identity, so it only has one element. But possibly you could have many other subgroups, right? Those are just the two that are always guaranteed. Right, so let's go over some examples of subgroups, because I think these are illustrative of the idea. this anymore. Okay, so some examples of subgroups. Let's do the first one. So the full group is going to be S3, or the symmetric group on 3 elements. And there's 6 elements total. So we have the identity, transposition that switches 1 and 2, transposition that switches 2 and 3, 1 and 3, then we have a 3 cycle, and the same 3 cycle squared. We haven't really talked about cycle decomposition notation, but it's kind of straightforward, so I would look it up on Wikipedia if you're a little confused, but the cycle notation just means that it's sort of like the other permutation notation, except this is a little bit simpler. It just tells you where every element goes in a cycle. So 1 goes to 2 here, 2 goes to 1, 3 is not listed, so it cycles to itself. Here 2 goes to 3, 3 goes to 2, and 1 goes to itself, and so on. You see here 1 goes to 2, 2 goes to 3, and 3 cycles back to 1, and so on. So S3 is the permutations of 3 elements, and there's 6 permutations total. We don't do anything. We swap 1 and 2, swap 2 and 3, etc., etc. So what is a subgroup? What is one of the subgroups of this full group? Well, I wrote down one example. We can look at the subgroup just generated by these 3 cycles. So one way of writing that is the subgroup generated by this element, like this. And that means that we take this element, and we take this element times itself, and then we take whatever the result of that is and multiply it by this again, and then by this again, and we keep doing that until we get back to the identity. And that creates what we call a cyclic subgroup. So here, one easy way, one surefire way to always get a subgroup of another group is to find the cyclic subgroup generated by one of the elements. So here I'm picking this 3 cycle, and we're going to generate a subgroup by multiplying this element by itself over and over. Right, so what happens here if we don't multiply this element any number of times, or like this to the 0th power is just the identity. So here it contains the identity. It contains this to the 1st power. If we just do this permutation once, then we just get that permutation. But also we could do this permutation twice. So if we do this permutation twice, then 1 goes to 2 with the first permutation, and then 2 goes to 3 once I apply it again. So in total, 1 goes to 3, 2 goes to 1, and 3 goes to 2. So it kind of skips one of the numbers. So here we get 1, 3, 2. And then you'll notice, actually, if you apply this permutation to this element again, or in other words, you get this is to the 1st power, this is to the 2nd power. If we get to the 3rd power, right, we actually get back to the identity. So that's kind of why it's called a cyclic subgroup. We go 0th power, 1st power, 2nd power, and then it cycles back to the 0th power, and then it kind of just goes in a cycle over and over. Right, so this is actually equal to 1, 2, 3 to the 0th power, but it's actually also equal to 1, 2, 3 to the 3rd power, and you get some sort of modular arithmetic going on here where every 3rd power is actually equal to the identity. So to the 0th power, 3rd power, 6th power, 9th power, etc. Right. So you get this 3-element subgroup of S3, which has 6 elements. And we'll write this down later, but it is important to notice now that 3 does divide 6, and we'll notice later that the size of any subgroup actually divides the size of the full group. So in this case, 3 divides 6, which is true. So we're never going to end up with like a subgroup of size 4 in a group of size 6, because 4 doesn't divide 6. And we'll be able to show later in a little bit that the size of the subgroup always divides the size of the full group. All right, so here's an example of a subgroup. It has size 3, full group has size 6, but it is closed under multiplication. Since every element is just a power of this element, you can show that it's closed under multiplication. It has inverses. Since the inverse of this element is this, the inverse of this element is this, and the identity is its own inverse. And what was the last property? So it's closed under multiplication. You can show that that's true. It contains the identity element, right, which is this element to the third power or to the 0th power. And it's closed under inverses because this element has this element in the subgroup, and this is the inverse of that, and vice versa, and the identity is its own inverse. So yeah, so it has the 3 properties. It is a subgroup, but like I said before, we can show more generally that when we generate a subgroup this way, it is always a subgroup. These special types of subgroups called cyclic subgroups. All right, and another quick example, number 2, before I erase this. If we look at the group of integers under addition, and then we look at the even numbers under addition, then those also form a subgroup. So we'll usually write that as 2z, like 2 times every number, all the even numbers, is a subgroup. And we'll also write subgroup sometimes this way, which is a less than or equal to sign, whereas the subset symbol is usually just a kind of like a semicircle with the line under it. So this is a less than or equal to sign. This means subgroup. 2z is the even integers under addition, and the statement is that this is a subgroup of all integers. All right. And in this case, it's actually a proper subgroup. It's not the trivial group, and it's not the full group. It's somewhere in between. And again, why is this an example of a subgroup? Why is this a subgroup? Well, it satisfies the 3 properties. It's a subset of this. It's closed under the product of the integers under addition, so the quote-unquote product. If I take any even numbers and I add them together, I get another even number. So it's closed under addition. 0 is an even number. It's 0 times 2, right? So 0 is the identity under addition. It's also contained in here. That was the second property. And then the third property is that it's closed under inverses. And if I have any even number like 2 times k, then negative 2 times k is also an even number. And so it's closed under inverses, meaning that if I have any even number, the negative of that number is also an even number, and it's contained in 2z. Okay, so it satisfies the 3 properties, and therefore the even numbers are a proper subgroup of all integers. So there's our 2 examples, and so here I picked one, was a finite group example where you had 6 elements in the group. The subgroup has 3 elements, 3 divided 6. In this case, you can't ask for division anymore because these are infinite sets, right? So it doesn't really make any sense to say that the size of this divides the size of this. They're both infinite. There's infinitely many even numbers, and there's infinitely many integers. Sorry, there's infinitely many even integers, and there's infinitely many of all integers, and therefore the division statement doesn't really make sense anymore. I think there is probably a statement, I believe there's a statement about cardinalities. If you get into set theory, like the cardinality of this, in this case, is the same as the cardinality of this, because there's like, you can show that this is a finite union of these sets. So if this is infinite, this has to also be infinite. But yeah, I don't really want to get too far into that. Basically, you have this statement about division, but it only makes sense in the finite case. All right. So yeah, Cayley's theorem, like I said, we're not going to prove it most likely, as that would take probably too much time for me to explain all the background behind everything to really prove it precisely. But I would like to do one of the problems in this book. So I showed you guys this book at the beginning of the last lesson. So this is Jacobson, Basic Algebra 1. Very good introductory book to abstract algebra for, I mean, even high school students could probably read this, but I would say more appropriately is probably like 3rd or 4th year of undergrad or beginning of graduate school. I mean, you probably should should have this mastered by the time you start graduate school. But right, so we're gonna look at page 39, and I like this problem. This is an interesting problem about Cayley's theorem. And if there is anyone in the chat who wants to ask a question, go ahead. Please do not hesitate if you are watching. Okay, so it's on page 39. It's the first exercise in section... this is at the end of the Cayley theorem section, which is 1.3. This is exercise 1, page 39. Exercise 1. So it says use a multiplication table, which we didn't really talk about, but I'll briefly go over what that is. So use the multiplication table for S3, which we just had listed up before. We said it had 6 elements. So use the multiplication table for S3 and the isomorphism from the Cayley transformation. Remember, we send every element to left multiplication by A, right? So A goes to this left multiplication bijection. And it says do this to obtain a subgroup of S6, which is isomorphic to S3. Right, so if you're watching this in the future, maybe you want to pause it and just look at this statement for a little bit, or look at this question. What is it asking, right? First of all, what is a multiplication table? Right, so for a group, or really for any set with a binary operation, you can always make a whatever the number of elements in the group are. In this case, there's 6. You can always make a 6 by 6 table, and you can explicitly write what is the product of each element. Like if I take A from the group, and I take B from the group, no matter what A and B are, I can just look at the chart and I find, what is my element on the left, what is my element on the right, and then it'll explicitly tell you what the product is. So in this case, there should be some 6 by 6 table that tells you how to multiply everything in S3. No matter which pairs of the 6 elements I pick, I can look them up in the table and find them in the table, and it should tell me what the result is of the product. So let's just do that real quickly. I already did it on my notes here, but I'll write it for you guys. And like I said, if you have to go back, if you're watching this later, please pause the video, maybe go back and reread the statement, or go in the book, page 39, exercise 1, and reread the problem. But I'm going to erase this now, and we're going to write down the multiplication table for S3, and then we'll answer this question. We'll try to figure out, okay, what is the subgroup of S6 that is isomorphic to S3 according to Cayley's theorem? So again, this is really a problem about Cayley's theorem. It's testing if you understand what is this isomorphism, and how does this allow us to view groups as embedded inside of symmetric groups. See, because S3 has 6 elements, and now we're showing a way in which it can sit inside S6, which 6 being the number of elements in S3. All right, so first we're going to write down the table, the multiplication table. Again, we said there's 6 elements, so it should be a 6 by 6 table. Try to make it big so it's easier to read. Okay, so we have 6 columns. And now we'll have 6 rows as well. One, two, three, four, five, six. 1, 2, 3, 4, 5, 6. Okay, so 6 by 6 row. We're going to write every element of the group on the top, and then we're going to write every element in the same order going down here. And then every box in the middle will be the product of the element on the left here with the product of the element on the left with whatever is here on the right. Don't know why I couldn't say that. So if we list the elements of S3, we have the identity permutation. We have the permutation that cycles 1, 2, and 3, cycles 1, 3, and 2, the transposition that swaps 1 and 2, that swaps 1 and 3, and that swaps 2 and 3. And these are all 6 elements, right? I can do nothing. I can cycle them this way, I can cycle them this other way, or I can just swap pairs that way. And that's all I can do. Those are the only permutations. And then every permutation is every composition of these permutation is another one of these permutations as well. So here I'm just writing the same elements. 1, 2, 3, 1, 3, 2. Again, this is cycle notation. This is not the permutation notation I was doing yesterday. So if you're confused about this, really quick Google will solve your problems. 1, 2 transposition, 1, 3 transposition, and 2, 3 transposition. And if I do the identity bijection and then I compose it with the identity afterwards, I still have the identity. So the product of these 2 elements is the identity. And since there's 36, I'm going to kind of I'll do the first row, but then I'm just going to write the rest in. Well, actually, the first row is kind of easy because every time we multiply by the identity on the left, it doesn't change anything, right? So first row should just be the same order as the elements themselves, because we're not doing anything. And then I'll do the second row, and then after that you'll kind of get the idea. So for the second row, this box is going to be this on the left composed with this on the right. So we're going to do identity first, then this, right? So if I compose the identity map with the cycle 1, 2, 3, I'm going to get 1, 2, 3. If I do the cycle 1, 2, 3, and then I do the cycle 1, 2, 3 again, I'm going to get the other cycle because it's going to go 1 to 2 and then 2 to 3. So it's actually going to go 1 to 3 and then to 2. If I do the cycle the other way, 1, 3, 2, and then I do 1, 2, 3, well, then they're actually inverses and they cancel each other out because 1 goes to 3, which then goes back to 1, 3 goes to 2, which then goes back to 3, and 2 goes to 1, which then goes back to 2. So this is actually, the product of these 2 is actually the identity. One thing that is important that you should be careful of is that you have to do the product in the correct order because a lot of these groups are not abelian, meaning that it matters which order you do the multiplication in. And so these elements here, I'm specifying these are always the elements on the left. These are always the elements on the right here. For this pair, it didn't matter because inverses, it doesn't matter which order you multiply them. You still get the identity, but for other elements, it will matter. And you'll actually get the wrong answer if you do it the wrong way. Hello, chatter. So we have about 10 minutes left, but I'm going over Cayley's theorem. We're writing out a multiplication table here. I'm doing the second row, and then I'm just going to fill in the rest. So this box here that we have to fill in, this means we do this transposition first, and then we do this cycle after. So first 1 goes to 2, 2 goes back to 1, so 1 doesn't go anywhere. 2 goes to 1, which then goes to 3, so 2 actually goes to 3. And 3 doesn't get sent anywhere by the first cycle, but it gets sent to 2 by the second cycle, so 3 gets sent to 2. 1 goes to itself, so we actually just end up with this transposition. And then similarly, here 1 goes to 3, 3 goes to 2, so here 1 goes to 2, and 2 goes to 1, 3 goes to itself. Oh wait, no, I did that wrong. Wait, 1, 3, 3 goes to 2. Oh, I did it wrong on my paper. 1, 3. Oop. Let me fix that. Okay, let me do it again just to be careful. So here 1 goes to 3, 3 goes to 2. So 1 goes to 2. 2 goes to itself, then 2 goes to 1. So 2 goes to 1. Yep, yeah, I had it wrong on my paper. And then here 2 goes to 3, 3 goes to 2, 2 goes to 3, 3 goes to 2, so 2 goes to itself, and 1 and 3 switch. But you'll actually notice that this is the only element left, and because left multiplication is a bijection, once we know what the other 5 are, we know that this has to be 1, 3. There's no other option. And let me fill, now I'm nervous, I made a mistake on the other ones, but let me just fill in what I have here and we'll check it. We'll try to check it. 1, 3, 2, identity. 1, 2, 3. 2, 3. 1, 2. 1, 3. 1, 2, 2, 3. 1, 3. Identity. 1, 3, 2. 1, 2, 3. And again, all I'm filling in here is I'm multiplying whatever the element here on the left is with the corresponding element on the right for whatever box that element is in. So here 1, 3 times the identity is 1, 3. The product of these two is 1, 2. 2, 3. 1, 2, 3. Identity. 1, 3, 2. 2, 3. 1, 3. 1, 2. 1, 3, 2. 1, 2, 3. And finally, any transposition multiplied with itself is always the identity. So here we get. So this table explicitly shows you what is the product of any two elements in this group. There's no questions about it. If you have a question, you want to know what's the product of any two elements, you just look them up in the table and you find out what the product is. So this is kind of like an explicit way to write down the binary product, or write down the function in some sense. You're explicitly telling where each pair of elements gets sent. So how does this, how do we think of Cayley's theorem? How does Cayley's theorem help us think of this as a subgroup of S6? Well, we have 6 elements here, and every time I multiply by on the left by each element, I get a different permutation of these 6 elements. So for instance, in the first row, I have a certain permutation, which is the permutation that doesn't change the top row. Then in the second row, I have a different permutation. For instance, the identity goes to this cycle. 1, 2, 3 goes to this other 3 cycle. This 3 cycle goes to the identity. This transposition goes to this transposition, and so on, right? You get remember, Cayley's theorem says when we multiply by something on the left, all that happens is we get some bijection of the elements, right? So we started with this order of the elements. We left multiplied by these 6 elements, and we got these 6 different permutations. So really all we have to do to answer this problem, right? The problem said, what is this group isomorphic to? Which subgroup is it isomorphic to of S6? Well, we can just rewrite this as elements of S6, right? The identity goes to this permutation, this goes to this permutation. So we have 6 different permutations in S6. An easier way to think of it is I can just relabel the names of these elements as 1, 2, 3, 4, 5, and 6, and then we would have our normal elements in S6, and I can sort of forget about everything. So all I'm saying is, in order to find what the subgroup is, I'm gonna relabel everything in terms of instead of writing them as permutations of these group elements, I'm just gonna say they're permutations of 1, 2, 3, 4, 5, 6, which is the elements. This is the first element. This is the second element. This is the third element, and so on. So again, if you don't have this chart, pause the video, write it down, or whatever you have to do. But I do have to erase this chart because it's too large. I can't write anything else down here. But we're gonna rewrite each of these left multiplications as a permutation, and those will be the 6 permutations that make up the subgroup of S6. So multiplying on the left by the identity gives us 1 permutation. Multiplying on the left by 1, 2, 3 gives us another permutation, and so on. We get these 6 permutations. And now we're going to just write down explicitly what those are in S6, and that will be our isomorphism. And I just have to remember to switch these two. Okay, so Cayley's theorem, according to this chart, where we're applying Cayley's theorem, Cayley's theorem says that the identity goes to this bijection in S6, which is the identity. Right, when I multiply on the left by the identity, it doesn't change anything. So we get the identity permutation in S6. Yes, I will save this stream. This will be on YouTube. Just look up Math Pond on YouTube, and you'll see this right after. So like I was saying, left multiplication by the identity gives you the identity bijection in S6. If you look at the table, it doesn't change any of the elements. If we left multiply by 1, 2, 3, then what happens is the identity gets sent to the second element. So we get the permutation 1, 2. The second element gets sent to the third element. The third element gets sent to the identity, which was the first element. So 3 goes to 1. The fourth goes to the fifth. And the fifth goes to, wait, that can't be right. Yeah, I think I did it wrong on the last one. I think these do have to change. So fifth goes to the sixth, and sixth goes to the, wait. Oh yeah, 1, 2, okay, yeah. Fifth goes to the fourth. No, that can't be right. Hold on. This chart is wrong. Let me just fix this chart. So 1, 2, 3, 4 goes to 5. Okay, sorry. So 1 goes to 2. Second element goes to the third element. The third element goes back to the identity, which was the first element. The fourth element goes to the fifth element. No. Fourth goes to the fifth, fifth goes to the sixth, and sixth goes back to the fourth. So, yeah. Fourth goes to the fifth, fifth goes to the sixth, and sixth goes back to the fourth. Right, so it's actually the product of 2 cycles. 1, 2, 3 is cycling here, and 4, 5, 6 is cycling over here. But it actually still, you can do some sort of checks in your head when you read these, because You know that there's certain properties of an isomorphism. Like for instance, when you take an element and you map it through an isomorphism, the order of the element, or in other words, the size of the cyclic subgroup that it generates, shouldn't change. So this is an element of order 3 because it's a 3 cycle, and this is the product of 2 3 cycles, and you can show that that element also has order 3 because if you do this permutation 3 times, that's the minimum number you need to get back to the identity. Right, so just continuing, we have the identity maps to the identity in S6. The 1 2 3 cycle maps to this product of 3 cycles in S6. 1 3 2 maps to a different permutation. So we look at the third row of the multiplication chart, and 1 goes to 2, 2 goes to 1. Or sorry. 1 goes to 3. 2 goes to 1. And 3 goes to 2. And we get a similar type of situation where we get a 3 cycle, but then there's another 3 cycle of the transpositions. So the first transposition goes to the last one, so 4 goes to 6. The second transposition goes to the first one, so 5 goes to 4. And then the last one's the sixth transposition goes to the fifth element, the second transposition. So 6 goes to 5, and that we actually had no other option here, right? Because it's bijection, so everything else mapped to everything besides 5, so 6 has to map to 5 here. And then continuing, so these are the first 3 elements. I'll try to fit this in here, so try to make 2 rows here. So now we have 1 2 transposition, and this maps to maps to 4, since the identity goes to 1 2 by left multiplication. The second element goes to the 6th. The third element maps to the 5th. The fourth element maps to the identity, which is the first. And the 5th maps to the 3rd. And again, we have a bijection, so now we know that 6 has to map to the only element left, which is 2. And we can check our chart and see that 2 3 actually does get sent to 1 2 3, which is the second element. Yep. So 6 goes to 2. I'm running out of room here, but I got 2 more here. Try to fit them in the corner here. So we have first element, second element, third element, fourth element. We also have the transposition 1 3. 1 3 maps to the bijection, which sends, again, if you don't look at the multiplication table, this is a little confusing, so you should go back to the table and make sure that all of these are correct. But multiplying on the left by 1 3 causes this particular bijection, which is 1 goes to 5, 2 goes to 4, 3 goes to 6. The fourth element maps to the second. And the fifth maps to the identity, which is 1. And then 6 has to map to 3 because that's the only thing left. And we check that that's true, and it is. And then the last one, sorry for the lack of space on the board, but we'll go over this in a second. So the last one, 2 3, multiplying on the left by this transposition 2 3 gives us this transposition of the elements, which it maps the first one to the last one, so 1 to 6. The second one maps to the fifth element. The third one maps to the fourth. Fourth maps to the third. The fifth maps onto 1, 2, 3, which is the second element. And then we're only left with one left. 6 has to go to 1, and it does. It goes to the identity. So explicitly here, we get our 6 elements of S6 through the bijection of Cayley's theorem. And Cayley's theorem basically says that these elements in S6 form a subgroup, and that subgroup is isomorphic to S3. So you have the identity in S6, you have this S6 permutation, this one, this one, this one, and this one. And if you really wanted to show that this was a subgroup, you would have to, again, show that these 6 elements in S6 are closed under composition. So when you compose the bijections, you always stay within these 6 elements. We showed that the identity is in here. Well, that's easy. The identity is right here. And then also that it's closed under inverses. And here, because it's an isomorphism, we actually know where the inverses are. So if this element maps to here, and this is the inverse of this element, then this has to be the inverse of this in S6. So you can show that for every element in this set in S6, it actually is closed under inverses. You can take any of these elements, and the inverse is somewhere else in this set. All right, so yeah, Ronaldo, thank you for chatting. If you have any more questions, we do have a Discord. I'll put it in here if I can. So that's the Discord. If you need any help, or you want to discuss any math problems, or just want to talk, you can go through there. I'm gonna, like I said before, I'm gonna put the video for today on YouTube. So you just look up Math Pond on YouTube, and it should be there. Let's see. Yeah, I didn't talk about cosets today. I prepared a little bit about cosets, so I guess we'll talk about that next time, but I think this is a good place to stop. This is a pretty hard problem. Again, this was page 39 in Jacobson in this book. Page 39, exercise 1. I think it's a very good problem, though. It shows you how Cayley's theorem allows you to explicitly get an isomorphism from an abstract group into a group of bijections of, if it's a finite set, it's bijections of some finite set to itself. So in this case, S6, you have 1, 2, 3, 4, 5, 6, and all the bijections of 1, 2, 3, 4, 5, 6 to itself form a group. And Cayley's theorem says that S3 is some subgroup of this because it has 6 elements. All right, so I'll just call it there. But again, if you have any questions, anybody in chat want to talk more, you can talk to me on Discord. You can talk in the chat now. But yeah, if you did show up, I appreciate anybody that did show up. And like I said, this will be on YouTube.